In this video, I'm going to try to summarize what a vector space is. So people who are mathematicians are going to have a much better sense of what this is. It's an idea from linear algebra, and it's getting into fairly sophisticated theoretical math, at least for those of us who just do physics and don't really do math. But we need to understand what a vector space is for quantum mechanics. And so my view of this is a little bit limited because I'm primarily thinking about this for quantum mechanics and not in general. But it's important to have a feeling for what this means and some of the properties of vector spaces, since we will be using them in quantum mechanics. So the idea is going to be that we have a vector space V, and there can be lots of different vector spaces, and especially in our traditional quantum mechanics work, we're often going to have two different vector spaces that we're working with. And we then have objects that live in our vector space. So you can think of a vector space as a collection of some sort of objects. We'll call those objects vectors. And there's going to be two properties that are defined for this vector space. One is addition. We can take any two objects in our collection, and when you add them together, we haven't defined what that means per se, but you get another object in that collection. Then there's something of scalar multiplication. So a scalar is, for instance, a number like 1 or square root of 2. It's not a vector, just a number, scalar. And we can multiply that by a vector, and again, we're going to get another object in the same vector space. Now, this right now might not seem like much of anything, but there's going to be a bunch of properties that result from this. So one thing that's true is that if our vectors u and v are a member of our vector space V, the sum of them also is. So I'm just going to write this as w vector, which was the sum, is in our vector space. And I'm trying to avoid using set notation, since not everyone who takes quantum mechanics really knows this advanced mathematical notation, which would be a shorter way to write this. So w is going to be in our vector space if u and v are in our vector space. And the reason that this matters is that if you have different vector spaces, we can't necessarily just add those vectors together. So the second property is that we can switch the order, and it doesn't matter. Now notice that this is for addition. So adding u plus v is the same as adding v plus u. And the reason it matters to say this is that it's not going to be true for multiplication, but it is true for addition. We also have an associative property. So let's say we want to add three different vectors together. We can add these two first, or we can add these two first. And they're going to be the same thing. So the order doesn't necessarily matter. We can switch them around and we can group them in different ways. Now, there's then going to be an object, which is basically our zero vector. So this is in our vector space, and it needs to be in every vector space. And it's defined so that when we add it to any vector, we get back our vector. So this is just 0. And what you might think about here is maybe our vector space is made up of two item vectors. We must have a 0, 0 item. Or if it's a 3-item vector, then it would be 0, 0, 0. But every vector space is going to have this 0 object. Now, we are also going to have basically the ability to create a negative. So for every vector u, we're going to have the negative of u. And that needs to also be in our vector space. And all this means is that if we add our negative vector, we get back our 0 vector. So the negative always needs to exist. We also have, going back to our scalar multiplication, that for any vector u, the vector that's created by this scalar multiplication is in our vector space as long as u was in our vector space. And the reason that's going to matter is, again, that means that if we can think about this scalar as being, for instance, maybe made up of the magnitude of this, so that when we normalize our vector, we know that our normalized vector is also in the vector space. So then we have a few scalar properties. So for instance, we have that if we have my scalar, so anything that I'm writing without the vector symbol, and that is being multiplied by the sum of these two vectors, I can just distribute it as you would want to. And again, it's worth writing these things down, since some of the properties you want to have exist for vectors doesn't necessarily exist. We then have the property that if we first were actually adding together two scalars and then multiplying, then we can in fact multiply it separately. Okay, so this was scalars, this was vectors. Finally, we have a multiplicative version of this, that if I have two scalars multiplied and then multiplied by a vector, this could be first multiplying one of the scalars by the vector. So you can either multiply the scalars first or one of the scalars by the vector. And then last, we have a property that basically there needs to be a 1. We have to be able to take 1, multiply it by our vector, and get our vector back. So these are the properties of a vector space. And again, we're writing them out. This is kind of a very theoretical math way to do it, to then really make proofs based on these properties. And for us, it's just worth thinking about some of the things that aren't on this list. And again, in quantum mechanics, this theoretical approach isn't going to be needed all of the time.